many more. And with the next operation of the next generation facility, especially after here, there are much more uncharted territories will be explored. Along with them, we'll have a lot of new phenomena. For example, in these light mass regions, there are some halo structures, some clustering nuclear string, neutron string, and spin, and so etc. And we go beyond the dripline, we have exotic decays like a two-proton decay, two-neutron decay, etc. And this is caused by the short-range nature of nuclear force, which means that when the system is imbalanced with protons and the neutron numbers, the valence nucleons will strongly coupled to continue and impacted by the environment. That is what we call this open quantum systems. And in this open quantum systems, exotic phenomenon occurs. So today, we are mainly focused on two kinds of exotic decays. First one is very specific to two-proton decays. In this part, we will briefly introduce how the structure will impact the decay properties, such as lifetime and nuclear correlation. And the second part, we will talk about the general decay properties of open quantum system, which is the non-exponential decay. In this part, we will propose three scenarios that might help future experimental studies to pin down this post-exponential decay. So let's first go to this two-proton decays. So ideally, a two-proton emitter ground state should higher than its daughter nuclei, but lower than its neighboring nuclei. In this case, the one proton emission is energetically forbidden or strongly suppressed. And the idea of two-proton decay is first proposed by Kodensky in 1960s. But experimentally, the first direct measurement was in iron 14-5 in 2002. So due to this development of time projection chamber, later on there are more two-proton emitters has been observed, like nickel 48, zinc, and kryptons. There are also some light nuclei who can be two-proton emitters, like barium 6, oxygen 11, oxygen 12. But because of the short lifetimes, it's really hard to directly measure these two-proton events. So far, there are a handful of nuclei have been discovered as the two-proton emitter, but theoretically, there are many predictions for these two-proton emitters, such as on the left-hand side figure, Eric using density functional theory to explore these two-proton candidates around the proton driplines. And later on, Leo used the uncertainty quantification, specifically the Bayes machine averages, to calculate the possibilities of two-proton emitters. And we can find that almost in all these nuclei beyond the proton driplines, there might be some possibilities to be a two-proton emitters. So there are a lot of two-proton emitters remains unknown and requires further experimental as well as theoretical studies. And the interest of the two-proton emitters also been boosted by the measurement of nuclear correlations. This is some observables can be measured directly from experimentally. So it's related to the asymptotic wave functions. And we can also extract some structural information from this nuclear correlation. So for example, in iron 45, they measured the opening angle of the two emitted protons, and it can be found out that most of the two protons are likely to emitted with small angles, which means they are likely to decay as a proton pair or diproton decay. And there are also small possibilities that these valence protons will emit with large angles. Also, in these light systems like barium 6 and oxygen neon systems, we can see that this angular and energy correlations varies from different systems to systems, especially when the system is in different shells. We can see dramatically different correlations. This means that in principle, the correlation is like the pairing correlation measured in experiment is like a fingerprint that can tell us some structural information about the nuclei. But since this pairing correlation is measured asymptotically, it's really hard to directly get this structural information. So this requires self-consistent model. But of course, this is a big challenge for theoretical studies because for this open quantum system, there are many different aspects we need to take care of properly. For example, the structural aspects, because this system are located near the dripline, so it often accompanied with exotic structures, and it is a decaying system, so we need to treat continue properly. And the last but not the least, so this two-proton emission is also a three-body decay. So this one need to take care of the three-body or few-body natures of the systems. And of course, there are many approaches in the market, but most of them are focused on one or two aspects. Right now, there's no comprehensive theories with the microscopic or self-consistent method that can deal with all the aspects. But of course, efforts have been made towards these directions. So today we are mainly focused on the model we developed like a few years ago right here. So it's named the Gamow-Kappa channel method, in which we try to combine the continuum effect and the three-body nature of the systems and try to explore the structural impact on these decay properties. So specifically, our model is three-body models and divide the system into three parts. So the core part and two valence protons. And as a result, the Hamiltonian can be written as the connected plus the pairwise interactions. And in order to consider the collectivities of the core, we also add core Hamiltonians. So as a result, the total wave function is constructed as the valence nucleons part plus a deformed core. And we use Jacobi coordinate to eliminate center mass motions to get the proper three-body asymptotes. Also, in the radius part, we use program basis, which contains bound state, resonance, and scattering state on the same footing, so we can treat the structure and decay informations. And in order to get the asymptotic correlations, one can also use this time evolution, time-dependent approach to propagate the systems to large space and time, so we can get the final state informations. But this is for the short-lived systems. For long-lived systems, this time-dependent approach can be time-consuming. So there's another way using this asymptotic wave functions. For example, we can use extract the asymptotic wave function directly from program basis, or use like transition metrics to get the final wave functions. And then we applied our models to study different two-proton emitters. So first is like light mass systems. So we have, in this case, we have successfully reproduced the experimental observations about the energy correlation and angular correlations. Meanwhile, we also have the experiments to pin down the spectroscopic in this oxygen 11, because experimentally they can only measure a broad resonance peak, but they don't know the details inside this resonance peak, whether it has multiple states. So of course, the theories can give some predictions, but in order to prove these predictions, we also compared the asymptotic correlations with the experimental observables. So we found that none of these individual states can reproduce the experimental correlations, but only if we mix them together, this one is well reproduced. So this has this proves that the resonance peak might contain different multiple states. And today we are mainly focused on this mid-heavy systems. So so far there are 4 two-proton emitters in these mid-heavy regions, like zinc, iron 14.5, nickel 14.8, zinc 15.4, and krypton 16.7. So why are we studying this place? Because as we see that these 4 emitters actually go across the PF shells, and some of them are located near the shell closures, but others are in this in the middle of the 2 shells, so might have some deformation effect. And this offers us a good opportunities to study the structural evolutions as well as its impact on this decay properties. Of course, there are many previous works has been done on these regions. For example, Greg Ranko uses 3-body models by assuming the configuration of those two-proton emitters and to analyze its decay lifetimes and as well as the nuclear calculations. Later on, Jimmy embed the continuum in the shell model calculations to see the competition between the one-proton and two-proton decays. Also, like Alice also did some work using hybrid models to take advantage of the configuration interaction and the spectroscopic factor or two-nucleon amplitude in this case, and also the three-body partial weights to estimate the configuration as well as lifetimes of these two-proton emitters. So in this talk, we will focus on our studies, which we revisit these regions to see how the decay properties as well as the structure in this region. So first, we calculate the angular correlation of the iron 14-5 and the nickel 14-8. So this tool is located near the shell closures, and there are some experiments data for this iron 45 angular correlations. And recently, there is a new measurement done by Bordeaux's group, and they add some more statistics above the previous experiments. So in our calculations, the angular correlation is, I would say, fairly produce the experimental values. And we found that actually this correlation is actually sensitive to the pairing interactions. And if we enhance the pairing interaction by 25%, then we will get dramatically different nuclear correlations. And but for nickel 14-8, the angular correlation looks like different. I mean, the large angle peak in nickel 14-8 is strongly suppressed. And in our calculation, this is probably because that in our calculation, iron 14-5 have some mixed between F wave and P wave. P wave we usually have two peaks, but in the nickel 14-8, this is more like a pure P7 configurations, which represent the shell closures in these systems. And this is kind of in accord with the three-body results done by Greg Ranko. He adjusted the P-wave components and found that when the weight of the P-wave components decrease, the second peak will suppressed in this case. And also we have done some calculations for this half-lifetimes and the nickel 14-8. So our calculation also suggests that in iron 14-5, it is have little P-wave components, so it's close to the F-wave limit. But in nickel 14-8, it's more like a pure F-wave configuration. So our calculated lifetime as a function of decay energies is just right on this F-wave limit. But experimentally, they suggest differently. So the latest experiments suggest that there might be like smaller decay energies and shorter lifetimes. And the latest experiment is kind of in accord with previous experimental studies as well as theoretical studies within the uncertainty. But of course, we know this half-life is quite sensitive to the decay energies and the configurations. So we might need future experimental and theoretical studies on this with high statistics and high resolutions to really draw solid conclusions for this progress. And then for those for those structures of valence protons, we calculate the density distributions in Jacobi coordinate. So the x-axis is the distance between two valence protons, and the y-axis is the distance between proton pair and the core. And in iron 45 and nickel 47, we found that both of them have 4 distinguished peaks. So this is actually a typical characters of F waves. But the difference is that in iron 45, this I mean both of them have a strong peak at this the right left-hand side, it corresponding to a diproton structures because the valence proton is relatively close. But in iron 45, the middle 2 peaks, which corresponding to a triangular shape, triangular structures is kind of suppressed. This is because, as we said, there are some P-wave components inside this iron 45, which makes the structure a little bit different from the pure F-wave components. As this is also in accord with shell models calculations. Also, but when we go to the heavier mass systems like zinc and kryptons, and we found that the deformations actually will impact these structures. So the deformation will bring actually mixing between different orbitals. So in these two cases, they have a certain amount of P-wave configurations. As a result, there's only two distinguished peaks in these two systems. And also this deformation will actually benefit for the formation of pairing nucleon pairs. So in Jacobi coordinate, we can see that there's large components for this S being equal to 0 pair formed in these two systems. So in our previous work, we've calculated the structure, the deformation impact on these decay properties, and we found that the deformation is actually crucial for this decay lifetimes of krypton 67. Because when the system is spherical, the valence proton is mainly occupied the F waves. And as a result, the calculated decay lifetime is much larger than the experimental measurement. But when the system becomes deformed, then there will be level crossings, and this P3 will be available for valence protons. As a result, it dramatically reduces the decay lifetimes. So this means that the deformation will benefit, will be crucial for this decay properties. The question is whether it will also impact the angular or energy correlations. And I think the answer is yes. According to our recent calculations, we found that if the system is deformed, that most of the valence protons will decay with large angles. But if the system is spherical, then this nuclear energy and nuclear angular correlations will be much different. So we really anticipate for future experiments that can measure some nuclear correlation in this region, and let us find out the inner structures and decay properties as in these kind of regions. And this is basically for the heavier mass two-proton emitters. But of course, this is not the end of the story. So when we look into the details of the angular nuclear correlations, sometimes we can find that this nuclear correlation is energy dependent. So for example, in this lithium beryllium 6 decay, two-proton decays, people found that as the decay energy increases, the energy correlation is kind of changes as the decay energies. So at that point, people didn't pay much attention on this aspect. They think this is because of the mix of the 2+ states, which pollute this data. But we will see that this might relate to some universal problems of the open quantum systems, which is well discussed in our second topic, that is the non-exponential decay. So before we talked about the two-proton decay, and of course there are many other decay modes like alpha, beta, gamma decay, and like fissions. All kinds of these decays show some universal properties. For example, in the classic point of view, we know that the decay have no memories, and the decay rates only depend on the amount of materials left. So that means that the survivabilities will obey exponential decay rules. And we can see that, for example, in this carbon-14, it have a very nice exponential decay curves, and it was widely used in this archaeology to pin down the years. So it's really something that people in mind. But in this quantum domains, this survival probabilities also can be can be described as the overlap between the wave functions at time t and the initial wave functions. And this is equivalent to this Fourier transformation of spectral functions. And it's not easy, not hard to find out that if this spectral function, I would say the spectral function is like the line shape of the resonance directly measured experimentally. And it's easy to find out that if this line shape obeys the Broad-Wigner distribution or Lorentz distributions, it will have an ideal exponential decay laws. But we know that this cannot be true in reality because this Broad-Wigner shape means it will have a symmetric shape, and the energy will go to infinity. But in reality, there is a threshold effect. So below the threshold is energetically forbidden for decays. So this threshold will distort this Broad-Wigner shape. And as a result, the decay cannot be always exponential in this open quantum domain. And normally in theory, we think that this decay can divide into 3 stages. So the first is the initial stage, in which the system needs some time to prepare itself because the quantum decay, they have some memory and entanglement or correlation effect that they know the history. And then the system will decay as a resonance. So it's have an exponential decay. So this one is in log scale, so it's a straight line. And in the end, there is another decay mode, which we call the governed by the power decay. So this power decay is happened in this long time period. And according to this Fourier transformation, this one is actually governed by the threshold in this low momentum limit. And how to understand this physics, in the physics, there's a naive but not very precise picture because each of the resonance have some weights due to the uncertainty principles. So there are possibilities that the particles will decay with a relatively high energy, and there are possibility the particle will decay with a relatively low energy. And these 2 different cases, they will have a different tunneling. They both need to tunnel through the barrier, but the difficulty is different. So for the high energies, it's easier, but for the low energy, it's harder. So there will be different decay rates. As a result, this long-term behaviors is governed by the scattering continuum, which is like a background. And so, of course, this attract a lot of experimental studies. And for the initial state, it has been already observed in this ultra-cold sodium atoms. In the survival probability measurement, they found that in this initial stage, this decay is not obey the exponential law. But for this long time period, the non-exponential decay has not been proved yet, because this is challenging for experiment as we can imagine. It needs a long period of time and a large amount of materials. So in these studies, we are trying to propose some scenarios that can help us help experiments to pin down this post-exponential decay. And so we used our time-dependent approach to deal with these problems. So propagate this resonance to large space and time, and to see how it will behave for the survival probabilities as well as the spectral functions. And thinking about the scenarios that can be used to pin down the non-exponential decay, we know that this is distorted by the threshold effect. So we are thinking that maybe dripline systems can help us fulfill these problems, because there are resonances in the dripline system that is close to the threshold, and on the other hand, there are large decay rates which will make the Broad-Wigner shape very distorted. So we are looking at the 9009, which is the 5 proton emitters discovered recently, and its mirroring system is helium-9, and whose ground state is like a virtual state, which is more like a scattering feature. So we think this might help us to to explore some probabilities, some properties of this non-exponential decay. So of course, experimentally have done some measurement on this nitrogen nucleus, and they found that the ground state has a 1 proton decay energy around 3 MeV, and its decay rate is like 600 keV. So it is compatible with each other. So might help us to pin down this post-exponential decay. And also there are some theoretical calculations done by George and Vitek using gamma fusion models to produce this energy spectrums. So in our case, we use our models to calculate the line shapes as well as the decay properties of the nitrogen. As a result, we can see this on the left-hand side figure is the spectral functions, which is the line shape of the nitrogen, and it is highly asymmetric. And the right-hand side figure is the spectral functions compared to the Brode-Wegener type. And we found that in the low energy region close to thresholds, there is a large discrepancy between the calculated spectral functions as well as the Brode-Wegener shape, because this one is much lower than the one. And when the decay energy increases, the line shape will restored to the Brode-Wegener shape. And we also found out this line shape is much dependent on this decay energy as well as decay rate. When the decay rate increases, the asymmetric of the shape, and the more unsymmetric of the shape is. So as a result, the calculated survival probability will have some non-exponential behaviors at the large period of time. And it also happens to other excited states of nitrogen, like the 1½ minus and the 5½ plus state. So this is really a universal properties for the open quantum systems. So and the dripline nuclei offers a good candidates for experimental to study this non-exponential decays. And so experimentally, they can directly measure this survival probability or measure these spectral functions and get the Fourier transformations to pin down this post-exponential decays. But of course, there are many challenges for these studies because the dripline systems are really hard to produce, and the statistics may be not enough for the right now. And so we are thinking about the other scenarios that can help us to pin down these post-exponential decays. So speaking about, so we realize that as we can see that the different states actually have slightly different decay behaviors. This is of course because of the different decay rates of the different orbitals, but also because of the states have different angular momentum or orbitals. This will result in different centrifugal barriers, and moreover, then this threshold behavior will be different. It will have a channel dependent. So each channels will have a slightly different line shape compared to the Brode-Wegener type. So we are thinking whether we can make use of this difference to help us pin down this non-exponential decay. So unfortunately, this is hard for 1 proton decay because in this 1 proton decay systems, the decay is usually governed by single channels. But what about the 2 proton decay systems? As we discussed that the 2 proton decay, it actually combines different single particle configurations. This means that in this single decay process, it might have different the different configurations will contribute. So this might help us to pin down the post-exponential decay. So as an example, we calculate the Brane 6 decay survival probabilities. So as expected, there will be plateaus at large time period, which corresponding to this powered decays. And moreover, the calculated spectral functions or the final state resonance peak contains multiple configurations as we expected. So these are different configurations in Jacobi coordinate, and they have also different line shapes compared to the broader Wegener type. This means that when we plot the survival functions as a function of decay energies, this the relative weights of the different configuration will change as the decay energy increases. So for example, at the low energies, the configuration C1 is dominated, but when the decay energy increases, this C2 will become dominated. And noticing that this final state configuration is actually directly determined the angular and energy correlations. This means that we might see some energy dependence in this nuclear correlations. So as a result, we cut this resonance peak into different slices, like 1, 2, 3, 4 regions, and we calculate its energy correlations. We found that as the energy increases, there is a peak developed at the small energy regions, which is in accord with the experimental studies in this Brain 6 case. So so we think that this we kind of understand these behaviors. So this energy-dependent angular correlation is actually related to this post-exponential decays because it causes the line shape different as a function of decay energies. So we can see this energy dependence in this nuclear correlations. On the contrary, it means that if experimentally they measure this nuclear correlation, energy-dependent nuclear correlations, it will help us pin down this post-exponential decays. And so this is the first the two scenarios that can help us study this post-exponential decays. And these two scenarios, actually, the line shape is all distorted by the threshold effect. But actually, this is not the only case that can distort the Wegener shape and cause the non-exponential decays. There are some other cases. For example, if there are two near-lying resonances with the same spin and parities, they can interference with each other. So in this case, it might also cause the non-exponential decay. To study these situations, we build an artificial helium-6, and we construct the two zero-past resonances. So one is dominated by P wave, another one is dominated by D waves. And we are pushing the close and close to each other, and to see how the decay properties will be like. And as we can see that when the two peaks are relatively far away from each other, they are kind of individually decays. So that they have a small interference, and the decay is much more like exponential decay. But when the two states are getting closer and closer, their line shape are interference with each other, and finally they are very distorted when they very close to each other. As a result, the survival probability is much more. There are large discrepancy between this exponential decay. And interestingly, we can see that one of those states decay much faster than the exponential decay. Another one is much slower. This can be understood by virtual transitions. And as we calculated in this figure, the overlap between the state 1 and state 2, we find that the transition between state 1 and state 2 are not equivalent. And some states are more likely to have a transition to another. So in this case, it's like the state 1 is will have a virtual transition to state 2 and then have a 2 neutron decay to the daughter nuclei. So in this case, it will distort, will impact this non-exponential decay and get a non-exponential decay. So this is the case for this near-lying resonances. Of course, helium-6 is an artificial system, but there are some realistic cases. For example, like in carbon-13 and nitrogen-13, we'll have some near-lying states that can be the candidates for the future experimental studies about this non-exponential decay. So basically, that's the main content of our talk. And so this talk we discussed about the two-proton decay, and we studied the structural impact on the decay properties such as lifetime and correlations. And we also discussed some universal properties about the non-exponential decays. And of course, we highly anticipate future experiments as well as theoretical studies can do some relative searches for these interesting problems. And thank you very much for your attention.
That's a very interesting talk. So, questions?
Please.
Very, very nice talk.
Thank you.
Topics are really interesting. I had a question on the survival amplitude calculation.
Yes.
So what exactly do you use for the initial stage? Is it compact in support, or is it actually something that extends out?
Yes, it's kind of compact. So first we calculate the resonance wave functions through our complex frameworks, and then we at some point we prepare the initial state by like a set of box size for that. And we also try to use the harmonic oscillator to expand these initial wave functions. And as it seems that it doesn't impact the survival probability very much. So I think this conclusion is solid for this calculation. Thank you.
How big is the box size?
So like right now it's 15 Fermis, and we also use a harmonic oscillator with some max like 14 shells, so to expand the wave functions.
More questions?
Oh yeah, please.
Yeah, I don't know if this on the first part of your talk. If you go back to slide 16,
Okay.
you have the very nice plots of nickel 48, I forget what they, 40 and iron 45 and so on. Do you know what it would look like if you did it in a different basis? If you projected onto intrinsic spin 0 and intrinsic spin 1, and you made these heat maps, what this would look like for these nuclei? Yes, you are right. I didn't prove that, but this is an interesting case because yes, so I think that this in Jacobi coordinate we can see something is related to the spin 0 because this Lx is equal to 0. Another one is equal to spin 1, but we don't know how the structure will look like. This will be an interesting aspect for the analysis, right? Please.
So in another slide,
yes,
the commercial transition, I found that it's a transition from the lower energy state to a higher energy state. So,
well, I don't know if this is a universal pattern, but in this case, probably because there's the lower states have the decay energy is small, so it's harder to directly decay. But on the other hand side, so usually the system will find an easy way to decay, to be like tunneling through the lower centrifugal barriers. So in this case, the overlap build a bridge from the state 1 to state 2. So they probably like to transit from the state 1 to state 2 and decay with a higher energy, which makes the decay much easier. Probably this is a reason, but I'm not sure if this is a universal pattern for that.
More questions? Any question in the chat? Yeah, I was so far it's quiet there.
Yeah, please.
Okay, I don't understand this very well, but do you expect this survival probability to have a similar feature for not only like two neutron or two-proton decays?
Yes, this is like a kind of universal properties for this open quantum systems. So it really doesn't matter where for two proton or two neutrons.
Are there maybe like easier decays that experiments can solve?
Well, I mean, the case for this is like we really need to find some near-lying resonance states that rarely exist in these realities. So this one is, for example, I think in this calcium 13 and the nitrogen 13 case, they have some near lying. I didn't remember. It's like a 1/2 plus or 3/2 minus, something like that. They are near lying with each other, and one can trying to study this phenomena.
About your two-proton decay project, gamma cup channel. So, for the theoretical side, what kind of improvements you are going to make the problem possibly
well, yeah, of course. Right now, our model is focused on this valence protons configurations. The treatment for the core is relatively rough. Right now, only have some collectivities inside. But of course, if we can microscopic describe of the core, how to say this co-excitations or different configuration mixing, that will make us make our models more robust for these studies.
I have a question.
Yeah.
So when you show this, the later time oscillatory behaviors, and it seems like there's a period oscillating, right? What is the physics for those?
I think it might be because at some phase shift, the state 2 and state 1 are matched to each other, and in this case, they are easily to transition from each other. And other cases, they are like orthogonals from each other, and then this transition is probably much suppressed, and then there will be some periodic behaviors for this. I think it's also can see in this overlap, so it's like some oscillations in this case.
More question. Yeah, Simin was really on time, so we actually have 20 minutes. Yeah, that is the first time this happened.
Okay.
But because you told us that there would be some meeting at 11 here.
But please, yeah, just think about like questions. What you have.
Yeah.
Especially students.
But Simin is still going to be here till Thursday.
Right.
So if you do not have questions now, try to find him later.
Yeah, sure, please.
Yeah.
Any questions? Well, just the Surrey Islands office. So it's just near beside the Silin's office.
Gotcha.
Yeah, so you mentioned the carbon 13 candidate. So you didn't have a chance to do calculations for that yet?
No, actually, no. This might not be a suitable case for our field body models, but it might be interesting for your gamma shell model calculation or more sophisticated configuration interactions.
Is it just because you would have a hard time picking a good core and valence?
Yes, yes. Okay. And usually, I mean, this near-line states might have some different structures or different configurations. So this is also hard to describe in our model.
Right. Okay.
So I have a 9 question.
Okay.
So here, these are time scales, right?
Yes.
It's actually possible to measure all these things in the real time in experiments.
Well, it depends on the decay rates of the systems, how large is the half-lives, and how much statistics we can get, right? So it's not I mean, it's more like a experimental problem, not rather than the theoretical problem, right?
Yeah, it's experimentation. Like you need to have extremely short time.
That's just a comment. So you are talking about measurements.
Yeah.
Right, so you would like to measure non-exponential limit. Right, you can either do things which are impossible, like Harry Norman and Berkeley people did, so extremely narrow resonances, for which half-lives are extremely long. You cannot go to 40 half-lives. okay, to see this concept of non-expression. So this is doomed to failure, right? But you can also do this measurements of spectral patterns.
Right.
But then the question is, how accurately do you want to measure it? So what is the noise limit?
Yeah, what is the energy resolution?
Right, exactly. And this is something which we are now trying to answer with the help of statistical methods, okay?
So do you know like a quick impression, what should be the energy resolution for this type of thing?
Right, exactly. So this is something which we are studying now with Simin, Pablo and Edgar, okay? So we'll perhaps be able to provide some useful information for experimentalists, how accurately should it be done?
Yeah, you can measure the energy of the final state.
Yes.
Yes, so I totally agree.
Can you go back 2 slides? I'm not.
Wait,
can you go
slide?
One forward down. One more.
No, okay.
So yeah, this slide.
Uh-huh.
So as I see, like where it gets to the scattering state, there's a lot of dips in the probability. Is that something in theory, or is that going to be expected through experiment, or do you know what that is?
Which one? You mean these oscillations?
Yeah.
Yeah, this is a theory calculation. Basically, it's like two kinds of mode interference with each others, and then this will cause these oscillations. But experimentally, I don't know if there will be enough statistics to see this oscillation.
Do you have any idea why with 1/2 plus it doesn't show that?
Well, I don't know. I mean, maybe because the one half plus state is the nature is like I mean it's the analog of the virtual state, which is already like a scattering features. So this transition kind of from a resonance decays to a scattering features is kind of smooth in this case. I think this might be the reason. Oh, please.
So you keep saying that it's a scattering feature, right?
Yes.
The helium line as well. You're saying the ground state is 1/2 plus. It is 1/2 plus, which is a scattering feature.
Well, I mean, this one we think is either threshold resonance or more like a scattering features in this one, because its analog state is like a helium line. The ground state is also 1/2 plus, but governed by this S waves. So we know that usually in this S wave, without the Coulomb barriers, it will become a virtual state. And the virtual state is not observable, but more like enhancement near the threshold for this cross sections. So it's more like a scattering features. That's why I'm saying this imaginary it could happen for the same reasons.
Okay, if you don't have more questions, thanks speaker.
Thank you. By the way, just an advertisement. So speaking of the statistics, we also going to have ISNET meetings at Fudan universities in November. But of course, the registration has passed the deadline. But if you want to participate, just let me know. So everyone is welcome. Thank you.
Yeah, so and then if you're interested in the dinner with speaker, let me know. Okay. For the night.那我觉得我们可以聊很多啊，就是那个刚创文章，
是都很多都很有意思，没有完全聊解。